We'll now explore this idea of polar opposites. And in order to do this, we need to consider the alpha less than infinity case. So alpha is a real number. There is a bound to how far apart 2 points can be. The idea of what we're doing here is, given a point A on some line L, we want to show the existence of a unique point, A star, on that line L, such that A star is equal to alpha. So we really want to show two things. First, that there is a point, A star, where the distance between A and A star is equal to alpha, and then that there's only one of these. We're going to start by showing the existence by considering the ray AW on line L. So W is just any other point on this line, and we're going to take the ray between A and W. We're then going to let A star be the point on the ray whose coordinate is alpha. We already said we have axiom 6, which says there is a one-to-one correspondence between a ray and the points between and including 0 and alpha, so there has to be a point who has a coordinate of alpha, and that will be A star. So we now have the existence of this point, but we also need to show that it is unique. We're then going to suppose there's a second point, P, on my line L, such that the distance between A and P is alpha, and P star is not equal to A. So if I take a ray between the point P and any other point on this line, that P star value given by the alpha coordinate is not going to be the same as A. Then there has to exist some point Q on the ray between P and A star, such that Q is between P and A star, so we have PQ A star, where Q is not equal to A. So we have 4 different distinct points, A, P, Q, and A star, all on my line L. So now I have to have one of these 4 betweenness relations with these points, either APQ, PAQ, QA A star, or QA star A. However, each of these has an issue. These first 2 right here, both would tell me that AP is less than alpha, since I have this other point Q even further along. And these second 2 would all tell me that AA star is less than alpha, since Q would be further along. So therefore, we have a contradiction. The only thing we've assumed is that this second point exists. So we have our contradiction, and we have to say the second point does not exist. So my A star value is unique. And this point A star that we just constructed is called the polar opposite of the point A. And allowing us to show this is unique gives us a couple of things. First, for any point B on my line L, such that the distance between A and B is greater than 0 and less than alpha, then I know that A star belongs to the ray between A and B. So no matter what point B I pick, if I take the ray between A and that point B, A star is guaranteed to be on it. In particular, if A is going to be my origin or my endpoint, A star will be the terminal point of this ray. This then gives us that for any point B, we have the betweenness relation A, B, A star. So every point B is going to be between A and A star. And once again, this is only for the case where alpha is less than infinity, for us the spherical case. So let's look at a couple of results from this. My first result says that if I have any 3 distinct points, A, B, and C, lying on a line L, then either I have the betweenness relation ABC, BAC, ACB, or BA star C, where A star is the polar opposite of A. And these cases are going to be mutually exclusive unless B is equal to C star. So if any of these pairs of points are going to be polar opposites, then it's pretty trivial that one of the first 3 cases will hold. If A and C are polar opposites, the first one's guaranteed to hold. If B and C are polar opposites, the second one's guaranteed to hold. And if A and B are polar opposites, the third one is guaranteed to be held. So we're going to assume that none of these are polar opposites and that all of their distances are going to be less than alpha. So let's start with the a equal to infinity case. So if alpha is finite, then we have this idea of what a star is. It's the polar opposite. But in the case that alpha is infinity, we can define a star however we see fit. And I'm going to let a star be chosen such that we have the betweenness relation AB a star, and the distance between a star and b is greater than the distance between b and c. If I'm in the less than infinity case, then I know by definition that I have the betweenness relation AB a star. So either way, whichever case I'm in, I do have the relation AB a star. Axiom 5 tells us how to insert a point C. So if I know that A, B, A star, and I have this extra point C, then I have to have one of these cases hold. Either C, A star, B, C is equal to A star, C, A star, C, B, BCA, or BAC. So this first case and this last case are allowed in our proof. We are claiming these should be one of the ones. So we're going to look at the other cases. So in the case that C is equal to A star, that will imply the case A, B, C, since if C is equal to A star, then A and C are polar opposites, so every point B has to be between them. Next, we'll look at the A star CB. So A star CB combined with the fact that we know A, B, A star would give us A star CBA according to our betweenness properties. But that also tells us that we have CBA or ABC as we want. And then finally, this one is also already included, although backwards, ACB. So therefore, every one of our possible cases do line up with these four cases. I'm not going to show that they're mutually exclusive unless B is equal to C star, but you can definitely check that. We do have a couple of corollaries to this. The first, if I have three distinct collinear points ABC, such that AB plus BC is less than or equal to alpha, then we know exactly one of these three relations hold, ABC, BAC, or ACB. So because of my previous theorem, all I really need to show is that the C A star B case can't hold in this particular case. So let's suppose it does. My betweenness relation would give me that C A star is equal to CB minus A star B. That would tell us that we have CB minus alpha minus AB, since A and A star are polar opposites. Rearranging things slightly, that's the same thing as AB plus BC minus alpha. However, we know that AB plus BC is less than alpha, so that would be a negative number. So the distance between C and A star would be less than 0, which is a contradiction. So that case cannot hold.